The purpose of this video is to review some important ideas about definite and indefinite integrals, which will be essential at the beginning of Calculus 2. So recall that the definite integral of the function f over the interval from a to b is written using this notation right here. We put x equals a down here, x equals b, f of x dx. This sign out here is called the integral sign. It's kind of an elongated s. The value of the definite integral is a number. It represents the signed area between the graph of f, the x-axis, x equals a, and x equals b. And signed area is not the same as area under the graph. We'll see why in just a second, because signed area is interpreted as negative when the graph is below the axis. And a word about notation: we never write the integral sign without the dx. For example, if I use notation like this, observe how I've left the dx out. It should be written with the dx. We can say this different ways. We can say the definite integral from x equals 0 to x equals 1 of x squared. We can say the definite integral from 0 to 1 of x squared. There's different ways of pronouncing this. We can also leave off the x equals here, the x equals there, just put a 0 and a 1. That's perfectly fine as well, but it is very important that the integral sign and the dx go together. Here's a simple example of a function. It looks something like this. This is minus 2 minus 1 up through 2. The integral from 0 to 1 of f of x would be the signed area bounded by the graph of the function, the x-axis, x equals 0 and x equals 1. So it's that area we're speaking of. And because the graph is above the x-axis, this signed area is positive. Let's say we look at the integral from 1 to 2 of f of x. From 1 to 2, observe how the graph is completely below. So the signed area, it would be the area bounded by the curve, the x-axis, x equals 1 and x equals 2. That's not the same as the area under the curve, because that would be down there. So we're speaking of that area, which is a signed area, which is interpreted to be negative because the graph is below. Let's say we are interested in the integral from x equals 0 to x equals 2 of f of x. That means we're looking at the signed area between the graph of the function, the x-axis, x equals 0 and x equals 2. We can see that we have positive signed area there, which appears to cancel with negative signed area there, so the value of the integral would be 0. Let's say we look at the integral from minus 2 to 2. We've got some positive signed area. We've got some positive signed area, yet that cancels with this negative signed area. So this is actually a positive number. In fact, it's no different than just that positive signed area right there. Should you see a green rectangle appear on the screen, that's just a property of the autofocus. Now, you may recall that the way we define the definite integral early in Calc 1 is to use what are known as Riemann sums. Here's a simple example of a function. In this case, I want to estimate the area between the graph of the function, the x-axis, x equals 0 and x equals 3. So I can do that by using a Riemann sum and dividing this interval up into rectangles. So I'm going to use 6 rectangles. So the width of each one is going to be 3 minus 0 over 6, which is 0.5. And I'm going to label the endpoints of the subintervals. x0 is 0, x1 is, that's a 0.5, x2 is 1, x3 is 1.5, x4, x5, and x6 is 3. Now, there's different ways we can construct our rectangles. I'm going to use a right-hand estimate, R6. Each of my rectangles will have the same base, delta x, which is 0.5. The way I get the height of each rectangle is I look at the subinterval, I start at the right-hand endpoint, I go up to the graph, and I draw a segment to the left. That's going to be the height. So let's say I look at that subinterval. I go start at the right-hand endpoint, go up to the graph, and then draw a segment to the left. So on and so forth. So I compute the areas of each of these rectangles and add them together. So I'll have f of 0.5 times delta x plus f of 1 times delta x, and the very last rectangle would be that height, which is f of 3 times delta x, which is 0.5. The first height, f of 0.5, is that value. It appears to be 1.5. The next rectangle would have a height of f of 1, which appears to be about 2. This one has a height that appears to be about 3.5, and so on and so forth. And the last height appears to be equal to 10. So I take each of those heights, and I'm going to multiply each of them by delta x, which is 0.5, and add them together, but I might as well just add them and multiply by 0.5 at the end. And if I do so, I get 14.75. And this is actually an overestimate of the true area, because each of these rectangles is including a little bit of area which is not part of the signed area between the graph of the function, the x-axis, x equals 0 and x equals 3. And that's because this function is an increasing function. Later in Calc 2, we'll discuss different methods of constructing sums using trapezoids, midpoint estimates, and so on and so forth. But this is just a brief reminder about how we actually define the definite integral. For certain types of functions, evaluating the integral is fairly easy if we just use our prior knowledge about area. So for example, here's a function that's defined between 0 and 6. It's piecewise linear, like this. If we want to compute the integral from 0 to 6 of this function, we can just break this down and look at the area of this triangle plus the area of that triangle. The area of this triangle is 1/2 the base, which is 3, times the height, which is 6. The area of that triangle is exactly the same thing, so the integral equals 18. Here's another example. Here's a semicircular function. So this is a semicircle. There's a radius of 3 here. If I want to integrate this function from -1 to 5, that's simply the same thing as asking what's the area of that semicircle. Well, the circle has radius 3, so the area inside the whole circle would be pi times 3 squared, but then we only want 1/2 of that, which is 9/2 pi. Now, of course, these are very simple figures, and much of Calc 2, at least early on, will be dealing with more difficult functions. But some important properties of the definite integral that we want to keep in mind before we go further. One is the summing constants rule. If we have a number times a function plus a number times another function, and we're looking at the integral of this quantity inside, we can break this up into 2 integrals and we can pull the constants outside. This is very useful. We call this the summing constants rules. It applies if we're adding, but it does not apply if we're multiplying. A very big mistake early on in Calc 1 and Calc 2 is to believe that the integral of the product is simply the product of the integrals. It didn't hold for the derivative. The derivative of the product is not the product of the derivatives. We had to use the product rule. It's not going to hold for integrals either. Additivity. If we are looking at the area bounded by the graph of the function, the x-axis from x equals a to x equals b, and we're adding to that the area bounded from b to c, it's the same as the area bounded from a to c. So we call this additivity. Now, the endpoint switching property. Usually we integrate from a smaller number to a larger number. I refer to that as the natural order of integration. But if we should be integrating from a larger to a smaller, that's the unnatural order as I call it, we can switch to the natural order simply by switching the endpoints and putting a negative sign out there. So for example, if we are computing the integral from 2 to 0 of f of x, that's the unnatural order. We can put a minus sign out there and to integrate from x equals 0 to x equals 2. Here's an example of that. Here's my graph of f. Let's say I'm considering the integral from 2 to 0 of f of x. That's in the unnatural order. I'm going from a larger to a smaller number. So I can put it back in the natural order, go from 0 to 2, as long as I put a negative sign there. Now the integral from 0 to 2 is this signed area, which is positive. So if I multiply that by -1, I get a negative quantity. On the other hand, let's say we look at the integral from 0 to 2. This is unnatural order again, because 0 is greater than -2. I can switch this to the natural order, go from -2 to 0, provided I put a minus sign out in front. Now let's take a look at the integral from -2 to 0. That's this signed area right here, which is already negative. So the integral from -2 to 0 is that signed area which is already negative. Put a sign out in front, a negative sign, and you get something which is in fact positive. So that's the definite integral. The indefinite integral we write using this notation. It's the same as the definite integral, except there aren't any numbers here or endpoints. Here we're using the integral sign to simply denote the family of antiderivatives. An antiderivative of a function little f is a function capital F whose derivative is little f. It's kind of like the opposite of the derivative. Now, from now on, we need to keep in mind that when we're trying to evaluate an integral, we need to look at it first and ascertain whether it's a definite or an indefinite integral. The indefinite integral is a family of functions. It's the family of antiderivatives. For example, the antiderivative of x squared would be 1/3 x to the third, because if we take 1/3 x to the third and compute its derivative, we would get x squared. But of course, we could add a 2, a 5, or anything, and that would also be an antiderivative. So we generally write the general antiderivative as 1/3 x to the third plus c, where c is a constant. So the indefinite integral of x squared would be the family of antiderivatives of x squared. The sum and constants rule still holds for indefinite integrals. We know lots of antiderivatives already, because we know from Calculus 1, we know lots of derivatives. We know from Calculus 1, for example, that if I take something like 5x plus 4, its derivative would be 5. In general, if I took the derivative of ax plus c, it would be a. So that means the integral of a would be the family of antiderivatives of a, which would be ax plus c. So for example, the antiderivative or the indefinite integral of 7 would be 7x plus c. And so we have a table of common antiderivatives, and each of these is obtained in the following way. Take what you have on the right, take its derivative, and you get what's inside the integral on the left. For example, if you take the derivative of 1 over n plus 1, x to the n plus 1 plus c, if you took the derivative of this, you'd bring the n plus 1 down, it would cancel with that, and you'd have x to the n. And that's precisely what we have inside the integral there. So we're going to call this the power rule for antiderivatives. And each of these comes from a derivative rule. For example, the derivative of sine x plus a constant is the cosine of x, which is inside there. The derivative of minus cosine plus a constant is the sine. So I'm going to refer to each of these, the set of functions in this table, as the list, and I want you to know each of these. Let's do an example. The indefinite integral of 5 square root of x plus 3 to the x minus 1 over 1 plus x squared dx. Now, is this a definite or indefinite integral? It's an indefinite integral, so our answer should be a family of functions. Now, the constant and sums rule says that because we're adding here, we can break this up into 3 separate integrals, and because this 5 is a constant, we can pull it through. Generally speaking, when we were computing derivatives, it was useful to change a root to a power. So we'll write the square root of x as x to the 1/2. 3 to the x minus 1 over 1 plus x squared. So we need an antiderivative of 1 over 1 plus x squared. We see in the table that the indefinite integral, or the family of antiderivatives of 1 over 1 plus x squared, would be the arctangent plus a constant. That minus sign is coming down there. The indefinite integral or family of antiderivatives of 3 to the x. 3 to the x. So in this case, a would be 3, so we'd have 1 over the natural log of 3 times 3 to the x plus a constant. Now we've already added a plus c in, so we really don't need to add another one. We can sort of glump them together. Now x to the 1/2, that's a power function. So if we want to integrate a power function, my n value is 1/2. If I add 1 to that, I get x to the 3/2, and then I divide by 3/2 out in front. So x to the 3/2, 1 over 3/2 times that 5. So here is my final antiderivative. Final antiderivative. Here's another example. The indefinite integral of x squared plus 5x plus 2 over x. No endpoints, so my result should be a family of functions. This function, between my fingers, is not on the list, but if I do a little bit of algebra, I can get something on the list. We can split this up. We can split up the numerator, so we'd have x squared over x plus 5x over x plus 2 over x. That simplifies to be x plus 5 plus 2 over x dx. And now we can split this up into 3 integrals. The integral, indefinite integral of x, 5, and then we can bring this 2 outside the last integral. I will just leave out the details, but if you go back and look at that table, the antiderivative of x would be x squared over 2. Antiderivative of 5 would be 5x, and an antiderivative of 1 over x would be the natural log of the absolute value of x plus c. Here are some things to keep in mind. There's no need to write a plus c for each of the individual integrals. They can be lumped together as one constant. We can always check whether our answer is correct simply by computing the derivative. Take the derivative of this. You might have to do a little bit of algebra, but it's the same thing up there. Now, the fundamental theorem of calculus is what connects antiderivatives to the definite integral. So initially, we can only estimate integrals, definite integrals, using Riemann sums, but the fundamental theorem provides us a shortcut. Let's suppose that we have a function little f which is continuous on the interval from a to b. That means that the function is well behaved, it doesn't have any jumps or holes or asymptotes. Let's suppose that capital F is an antiderivative. That means that the derivative of capital F is little f. Then the integral, the definite integral from a to b of little f, is what you get when you substitute b and a into the antiderivative and subtract. It allows us to compute the definite integral exactly. Now, a function has lots of antiderivatives, but typically we use just the simplest one where c is 0. So here's an example. The integral from 1 to 3 of x squared dx. This is a definite integral, so the answer should be a number. Now we know that an antiderivative of x squared from the table, using the power rule for antiderivatives, is 1/3 x to the third. That's because the derivative of that is x squared. So here's our antiderivative. We need to substitute 1 and 3 in and subtract. I'm sorry, this should be a 2. I meant for that to be a 2. So we substitute 1 and 2 in and subtract. That's what this vertical bar means. And if we do so, we get 7/3. That's exact. A few comments. The vertical line simply means take the expression 1/3 x to the third, substitute 2 and 1 and subtract. It is at this stage when we've computed the antiderivative and substituted in the endpoints, that's when the integral sign and the dx, they disappear simultaneously. It's easy to check that if we used a different antiderivative like 1/3 x to the third plus 5 or plus c, we would still get 7/3 because of the cancellation. That's why we always use the simplest antiderivative where c is 0. We can also check whether our answer is reasonable by graphing the function x squared on the interval from 1 to 2. The graph is going to be above the x-axis, which means the signed area should be positive, which it is. It is 7/3. Another example. The integral from 0 to pi over 6 of sine of x dx. Now, going back to the table from a previous couple pages ago, the antiderivative of sine of x is minus the cosine of x. That's the antiderivative. The derivative of sine would be cosine, but we want the antiderivative. So, to get the definite integral from 0 to pi over 6, we take that antiderivative, we substitute 0 and pi over 6 and subtract. Now we have to be a little bit careful here about the negative signs. So we're going to take minus the cosine, substitute pi over 6, and then we're going to put a minus sign there, and then we have to substitute 0 into this. So we have minus cosine of 0. The cosine of 0 is 1, so we'd have a plus 1, and then the cosine of pi over 6 with a negative sign out in front is minus root 3 over 2 plus 1. This is an exact value. Here's an example, some examples I'd like for you to do in preparation for class. I have a piecewise defined function like this. It consists of 3 semicircular arcs followed by a linear segment. I would like for you to find the exact values of the following: the integral from 0 to 4 of f of x dx, the integral from minus 4 to 4 of f of x dx, the integral from minus 6 to 8 of f of x dx, and the integral from 0 to negative 6 of f of x dx. Now, exact values mean we don't want to use calculator approximations. You'll have lots of pi's floating around. For example, if you had something like pi plus 1, just leave it as it is. That's fine. And then here are some integrals. X equals pi over 4 to pi over 2 sine of x dx. The integral from 1 to 4 of x plus the square root of x. Do these exactly. You're going to have to know a little bit of trigonometry. And then the integral of 2 to the x plus x squared plus 1 over x dx. Now, this integral is indefinite, so your answer should be a family of functions. You'll want to refer back to the list. You might need to do a little bit of algebra. These two integrals are going to be definite integrals, so your results should in fact be just numbers. So do these in preparation for class.